Right now, somewhere in a distant galaxy, a dying star is about to unleash more raw power in 10 seconds than our sun will produce in its entire 10 billion year lifetime. Tonight, we're diving deep into the most extreme forces in existence, from explosions that outshine entire galaxies to invisible energies, ripping the fabric of reality apart at the seams. But here's the thing. What you think is the most powerful force in the universe might shock you because the answer isn't what most people expect. If you want to discover cosmic power beyond imagination and see forces that make nuclear bombs look like birthday candles, smash that like button and hit subscribe because this journey is about to get wild. We're starting with something that exists inside every single atom in your body right now. And it's 100 trillion times more powerful than gravity. Prepare yourselves. We begin. Deep inside every single atom in your body right now, there's an invisible war happening that most people never think about. And this war is being fought at a scale so impossibly small that it makes a grain of sand look like an entire planet. Inside the nucleus of each atom, protons are packed together so tightly that they're practically touching. And here's where things get weird, because these protons all carry positive electrical charges. And just like when you try to push the north poles of two magnets together, they should be repelling each other with absolutely tremendous force. The electromagnetic force between these positively charged particles is so powerful that it should rip the nucleus apart instantly, sending protons flying away from each other at incredible speeds. Yet somehow, they stay locked in place, bound together in a space smaller than anything you could possibly imagine. What keeps them there is the strongest force in the entire universe, a power so intense that it makes every other force look pathetically weak by comparison. And scientists call it the strong nuclear force. This force operates at distances smaller than a single proton, which is already incredibly tiny at about 1/10 trillionth of a meter across. And at these impossibly small scales, the strong force is absolutely dominant, measuring in at roughly 100 times stronger than the electromagnetic force that governs chemistry and electricity. But that's just the beginning of how powerful this force really is. Because when you compare it to the weak nuclear force, which handles radioactive decay, the strong force is about 1,000,000 times more powerful. And when you stack it up against gravity, the force that holds planets in orbit and keeps your feet on the ground, the strong nuclear force is approximately 100 million trillion times stronger. Think about that number for a second, because it's almost impossible to comprehend. If gravity were a whisper so quiet, you could barely hear it even in perfect silence, then the strong nuclear force would be a thunderclap, so loud and so powerful that it could literally shatter mountains into dust. The strong force achieves this incredible binding power through particles called gluons, which act like invisible chains connecting the fundamental building blocks of matter called quarks. And here's where things get even more fascinating, because gluons don't behave like any other force carrier in nature. When you try to pull two quarks apart, instead of getting weaker with distance like gravity or electromagnetism, the strong force actually gets stronger the more you try to separate them, almost like stretching a rubber band that somehow grows thicker and more resistant with every single inch you pull. Scientists call this bizarre behavior confinement, and it means that you can never isolate a single quark, no matter how much energy you pump into the system, because the harder you try to rip quarks apart, the more the strong force fights back, until eventually the energy you've added simply creates brand new quarks and gluons, instead of separating the original ones. It's like trying to cut a chain in half, only to watch it magically grow new links, right where you made the cut, reforming itself instantly, and rendering your efforts completely pointless. Inside each proton, 3 quarks are locked in a dance of pure energy, bound together by these gluons in a prison that can never be broken. And what makes this even more mind-blowing is that the gluons themselves carry the strong force, which means they can interact with each other and create an incredibly complex web of connections that even our most powerful supercomputers struggle to model accurately. The strong force operates on scales so microscopically small that even a femtometer, which is 1/4,000,000th of a meter, seems absolutely vast by comparison. And at these distances, where the force does its work, the familiar world of everyday physics that we experience completely breaks down and stops making sense. Space and time themselves become uncertain and start fluctuating wildly according to the strange and counterintuitive rules of quantum mechanics, where particles can be in multiple places at once, and reality itself seems to exist in a state of constant probability rather than certainty. This fundamental force shapes the very building blocks of all matter in the universe, determining which atomic nuclei can actually exist and which combinations are impossible, and it sets the rate at which stars burn through their nuclear fuel, controlling the balance between creation and destruction in the hearts of every single star scattered across the infinite cosmic void. Without the strong nuclear force holding everything together, protons would instantly fly apart due to their electromagnetic repulsion. Atomic nuclei could never form in the first place. Fusion reactions in the cores of stars would never begin, and the universe would contain nothing but individual hydrogen atoms drifting through space alongside free electrons, with no possibility of creating anything more complex. The strong force also determines how stable different atomic nuclei are, which is why some elements like iron are incredibly stable, while others like uranium are radioactive and decay over time. And this stability depends on the delicate balance between the strong force trying to hold nucleons together and the electromagnetic force trying to push protons apart. For lighter elements like helium and carbon, the number of protons and neutrons in the nucleus is roughly equal because the strong force can easily overcome the relatively weak electromagnetic repulsion between just a few protons. But as you move up the periodic table to heavier elements, you start to see more and more neutrons compared to protons, because each additional proton adds more electromagnetic repulsion, while each neutron contributes to the strong force without adding any repulsive charge. This is why platinum has 78 protons, but 117 neutrons, and rutherfordium has 104 protons, but a whopping 157 neutrons, because without those extra neutrons providing additional strong force, these heavy nuclei would rip themselves apart instantly under the intense electromagnetic repulsion of all those positively charged protons crammed into such a tiny space. The strong force is carried out through the principles of quantum chromodynamics, which is one of the most successful but also most complex theories in all of physics. And despite its name suggesting color, it has nothing to do with actual visible colors, but instead uses color as a metaphor for a type of charge that quarks and gluons carry. Quarks come in 3 color charges that physicists whimsically named red, green, and blue, while antiquarks carry corresponding anticolors. And the fundamental rule of quantum chromodynamics states that all observable particles must be color neutral, meaning the colors must cancel out to white. Just like mixing red, green, and blue, light produces white light. This is why quarks are always found in groups of 3, inside protons and neutrons, because 1 red quark plus 1 green quark plus 1 blue quark equals a color-neutral particle that can exist in our universe. And it's also why you can have pairs of quarks and antiquarks in particles called mesons, because a color and its corresponding anticolor cancel each other out perfectly. The mathematics behind quantum chromodynamics are so incredibly complicated that exact solutions are virtually impossible to calculate for most situations, and scientists have to rely on massive computer simulations that can take months or even years to run on supercomputers just to predict how quarks and gluons will behave in different scenarios. One of the most counterintuitive aspects of the strong force is that it actually grows weaker when quarks are extremely close together, a phenomenon called asymptotic freedom, which earned its discoverers the Nobel Prize in Physics, because it was such a revolutionary discovery that completely changed our understanding of how matter works at the deepest level. When quarks are pressed right up against each other at incredibly high energies, they behave almost as if they're free particles that barely interact at all. But the moment you try to pull them apart and increase the distance between them, the strong force kicks in with overwhelming power and prevents any separation from occurring. This strange behavior is completely opposite to how we experience forces in everyday life, where things generally get weaker with distance. But in the quantum world of quarks and gluons, the rules are fundamentally different and often defy our intuition. Built from observing the macroscopic world, the strong force is also responsible for the binding energy that holds atomic nuclei together. And this binding energy is so enormous that it accounts for most of the mass you see in ordinary matter through Einstein's famous equation relating energy and mass. When you look at a proton, the 3 quarks inside it actually contribute only about 1% of the proton's total mass, and the remaining 99% comes entirely from the energy of the strong force field binding those quarks together, which gets converted into mass through the equivalence of mass and energy. This means that almost all of the mass in your body, in the chair you're sitting on, in the planet Earth itself, doesn't come from the mass of fundamental particles, but rather from the pure energy of the strong nuclear force, doing its job of holding quarks together inside protons and neutrons. The range over which the strong force operates is absolutely critical to understanding why it works the way it does, because this force extends only to the edge of an atomic nucleus, which is about 1/10 trillionth of a meter, or roughly 1/10,000th the width of a human hair. Beyond that incredibly tiny distance, the strong force drops off so rapidly that it becomes essentially zero, which is why atoms can exist at all, because if the strong force had a longer range, it would pull atoms together and prevent molecules from forming, making chemistry and biology completely impossible. This extremely short range also explains why nuclear reactions release so much more energy than chemical reactions, because you're directly manipulating the strong force, which stores vastly more energy than the electromagnetic force that governs chemistry. And this is precisely why nuclear fuel has approximately 1 million times the energy density of fossil fuels like coal, oil, or natural gas. When uranium atoms undergo fission in a nuclear reactor or a nuclear weapon, they're releasing a tiny fraction of the binding energy that the strong force has stored in the atomic nucleus. And even that small fraction is enough to power entire cities or level them completely, depending on how that energy is released and controlled. The strong force also plays an absolutely crucial role in nuclear fusion, which is the process that powers every star in the universe, including our own sun. And without the strong force, fusion would be completely impossible, because protons would never be able to get close enough to stick together and form heavier elements. Inside the core of the sun, temperatures reach about 15 million degrees Celsius, which gives hydrogen nuclei enough kinetic energy to overcome their electromagnetic repulsion and get close enough for the strong force to take over and bind them together. And when this happens, a tiny amount of mass gets converted into an enormous amount of energy that radiates outward and eventually reaches Earth as the sunlight that makes life possible. The strong force sets an upper limit on how heavy atomic nuclei can be before they become so unstable that they fall apart on their own. And this limit occurs somewhere around element 118 on the periodic table, beyond which nuclei simply cannot hold themselves together, even with the strong force working at full power, because the electromagnetic repulsion from having so many protons in such a small space becomes overwhelming. Scientists have been trying to create super heavy elements beyond this limit by smashing lighter nuclei together at incredibly high speeds, hoping to find an island of stability where certain combinations of protons and neutrons might be stable for longer periods. But so far, These super heavy elements decay almost instantly after being created, existing for mere fractions of a second before splitting apart. The strong force is also intimately connected to one of the biggest mysteries in physics, which is why there's more matter than antimatter in the universe. Because in the first moments after the Big Bang, when the universe was incredibly hot and dense, quarks and antiquarks should have been created in equal numbers, and they should have annihilated each other completely, leaving nothing but pure energy. The fact that we exist at all means there must have been some tiny asymmetry in how matter and antimatter behaved under the influence of the strong force and the other fundamental forces, leading to a slight excess of matter over antimatter. But physicists still don't fully understand what caused this asymmetry or why it occurred in the first place. Despite being the strongest force in nature by an absolutely enormous margin, the strong nuclear force has what you might call a fatal weakness, which is its incredibly limited range, because beyond the tiny realm of the atomic nucleus, the strong force might as well not exist at all, since it drops to zero so quickly with distance. This means that on larger scales, from atoms to molecules to planets to galaxies, the strong force plays no direct role whatsoever, and other forces like electromagnetism and gravity take control instead, shaping the structure of matter and the universe in ways that the strong force never could. Despite being so much more powerful at short distances, in the extreme environments of neutron stars, which are the collapsed cores of massive stars that have exploded as supernovae, matter is compressed so densely that atomic nuclei are crushed together and dissolved, with neutrons packed so tightly that the entire star becomes essentially one giant atomic nucleus held together by the strong force. These neutron stars pack more mass than our entire sun into a sphere just 20 kilometers across, creating densities so extreme that a single teaspoon of neutron star material would weigh about 6 billion tons on Earth. And the strong force is the only thing preventing these objects from collapsing even further into black holes, where not even the strong nuclear force can resist the pull of gravity. The study of the strong force has led to the development of some of the most sophisticated experimental facilities ever built, including massive particle accelerators, like the Large Hadron Collider at CERN, where scientists smash protons together at speeds approaching the speed of light to create conditions similar to those that existed in the first moments after the Big Bang. By colliding particles at these extreme energies, physicists can probe the behavior of quarks and gluons in conditions where the strong force operates differently, testing the predictions of quantum chromodynamics and searching for new phenomena that might reveal deeper layers of reality beyond our current understanding. One of the most remarkable aspects of the strong force is how it demonstrates that strength and range are inversely related in fundamental forces, because while the strong force is by far the most powerful, it also has by far the shortest range, whereas gravity is the weakest force by an almost incomprehensible margin, but has infinite range and can affect objects across the entire observable universe. This inverse relationship between strength and range is one of the deep patterns in physics that hints at underlying principles we don't yet fully understand, and it raises profound questions about why nature is structured this way, and whether there might be some deeper explanation connecting these apparently separate properties. The strong force also connects directly to the mystery of confinement, which remains one of the unsolved problems in theoretical physics, even though we can observe its effects clearly in experiments. Because while quantum chromodynamics predicts that quarks should be confined inside hadrons like protons and neutrons, nobody has been able to prove mathematically from first principles why this confinement occurs or derive it rigorously from the basic equations of the theory. Solving the confinement problem is considered so important that the Clay Mathematics Institute has offered a $1 million prize to anyone who can provide a rigorous mathematical proof explaining why quarks are permanently confined. And despite decades of effort by some of the world's most brilliant physicists and mathematicians, the prize remains unclaimed because the problem is just that difficult and that fundamental to our understanding of how the universe works at its deepest level. Yet despite its incredible power and the essential role it plays in making matter possible, the strong nuclear force has a reach that extends only to the very edge of an atomic nucleus, and beyond that microscopic realm, measuring roughly 1 femtometer across. Other powers take control and shape the cosmos in completely different ways, which means that to truly understand the most powerful things in the universe, we need to look beyond the quantum realm of quarks and gluons and venture out into the vast expanse of space, where different kinds of power manifest on scales that dwarf anything happening inside atomic nuclei. Jiwa. Somewhere in the cosmos right now, billions of light years away from where you're sitting, a beam of pure concentrated energy is tearing through the fabric of space at nearly the speed of light. And for just 10 seconds, this cosmic laser will release more raw power than our sun will produce in its entire 10 billion year lifetime, from birth to death. This is a gamma ray burst, and it represents the most powerful explosion that the universe can create through natural processes, an event so violent and so energetic that it makes every other cosmic phenomenon look gentle by comparison. These titans of destruction occur when the most massive stars in existence, giants containing anywhere from 20 to 100 times the mass of our sun, finally run out of nuclear fuel after burning through their stellar reserves at a rate that would consume our sun's entire energy supply in just a few million years. Instead of the 10 billion years our sun will last. When these monsters exhaust their fusion reactions and can no longer generate the outward pressure needed to resist their own crushing gravity, the result is not just a simple collapse, but rather the most spectacular death scene the universe has to offer, a catastrophic implosion, followed by an explosion that can be detected from literally the other side of the observable universe. The star's core, which has been fusing lighter elements into heavier ones throughout its entire life, suddenly finds itself unable to continue because it has created iron in its center. And iron is the end of the line for fusion reactions, since fusing iron actually consumes energy instead of releasing it. Without that constant outward push of energy from fusion to hold the star up against gravity's relentless pull, the core collapses in on itself faster than you can blink, plummeting inward at speeds approaching 1/4 the speed of light and compressing matter to densities that exceed anything found anywhere else in the universe, except inside black holes themselves. In less than a second, a core the size of Earth, containing more mass than our entire sun, gets crushed down to a sphere just 30 kilometers across. And this catastrophic compression creates a shock wave that tries to blast its way back outward through the star's outer layers. But that's not where the gamma ray burst comes from, because the real action happens at the very center, where gravity has won the ultimate battle. As the core implodes beyond the point of no return, it crosses the event horizon and becomes a black hole. But this is not a peaceful transition, because the star was rotating when it died, and that rotation gets amplified enormously as the core shrinks down according to the conservation of angular momentum, the same principle that makes figure skaters spin faster when they pull their arms in close to their body. The newborn black hole finds itself surrounded by a swirling disk of superheated material that couldn't quite make it into the black hole on the first pass. And this accretion disk is rotating so fast that matter near its inner edge is traveling at significant fractions of the speed of light, whipping around the black hole multiple times per second while being heated to temperatures of billions of degrees. Magnetic fields that were present in the original star get twisted and amplified by the disk's rapid rotation until they reach strengths that are almost incomprehensible. And these fields get wound up like springs being coiled tighter and tighter until they can't take any more stress. And when they finally snap and reconnect in a process called magnetic reconnection, they release an absolutely staggering amount of energy in the form of two narrow jets that shoot out from the black hole's north and south poles. These jets are unlike anything else in nature because they're so tightly focused and so energetic that they act like cosmic drill bits pouring through the collapsing star at 99.9% of the speed of light and carrying enough energy to power our sun for several billion years, all concentrated into a beam that's narrower than the star itself. The material in these jets is accelerated to such extreme velocities that relativistic effects become impossible to ignore, and time dilation means that matter in the jet experiences time passing at a completely different rate compared to stationary observers, while the energy of individual particles gets boosted to levels that make our most powerful particle accelerators look like children's toys. When the jets finally punch through the star's outer layers and burst into open space, they create the gamma rays we detect as gamma-ray bursts. And these bursts shine with such incredible brightness that if you could see gamma rays with your naked eyes, they would appear brighter than the full moon, even from galaxies billions of light years away. Think about what that means for a moment, because the moon is only about 384,000 kilometers from Earth, while these gamma-ray bursts are occurring at distances measured in billions of light years, where 1 light year alone equals about 9.5 trillion kilometers, and yet they still appear brighter than that relatively close moon when viewed in gamma-ray wavelengths. The energy released in just a few seconds of a gamma-ray burst exceeds what 10 trillion hydrogen bombs would produce if they exploded every single second for the entire current age of the universe, which is about 13.8 billion years. And that comparison still doesn't really do justice to the sheer magnitude of power being unleashed, because we're talking about energy levels that transcend human experience by such an enormous margin that they become almost meaningless to contemplate. The most powerful gamma-ray burst ever detected by human instruments earned the nickname the Boat, which stands for brightest of all time, and this monster occurred in October of 2022 when it slammed into Earth's upper atmosphere with such intensity that it saturated gamma-ray detectors across our entire solar system and temporarily altered the chemistry of Earth's ionosphere from a distance of 2 billion light years away. To put that in perspective, imagine standing on Earth and watching a flashlight beam from the star system Alpha Centauri, which is about 4 light years away, and having that flashlight appear as bright as a car's headlight shining directly in your face. That gives you some sense of the impossible power that gamma-ray bursts possess, though even that comparison falls short of capturing the true scale of what's happening. Scientists estimate that the boat released as much energy in just a few hundred seconds as our sun will produce over its entire 10 billion year main sequence lifetime, and all of that energy was concentrated into 2 narrow jets that happened to be pointing almost directly at Earth, which is the only reason we could detect it with such clarity, because gamma-ray bursts are highly directional, and if the jets are pointed away from us, we might not see them at all, despite the enormous energy being released. The light we detect from these ancient explosions has been traveling through space for billions of years, crossing incomprehensible distances while the universe continued expanding and galaxies continued forming and dying. And by the time those gamma rays finally reach our satellites and telescopes, they're carrying news of stellar deaths that occurred when the cosmos was young and the first generation of massive stars were living fast and burning bright before exploding in these catastrophic events. Some gamma-ray bursts we've detected are so distant that their light began its journey less than 1 billion years after the Big Bang, when the universe was still in its infancy and the first large-scale structures were just beginning to form. And these ancient beacons give us glimpses of what the early cosmos was like, when stars were generally more massive and more prone to violent deaths than the stars we see in the nearby universe today. The jets created by gamma-ray bursts maintain their narrow focus across distances that dwarf anything in human experience, traveling for hundreds of thousands of light years, while remaining so tightly collimated that they appear as thin lines, even when viewed through our most powerful radio telescopes. And this incredible precision is achieved through a combination of magnetic fields and the relativistic effects that occur when matter moves at speeds approaching the fundamental speed limit of the universe. The mechanism that keeps these jets focused is still not completely understood by astrophysicists, but it likely involves something called magnetic collimation, where twisted magnetic field lines act like invisible walls that channel the jet material into a narrow beam and prevent it from spreading out into a wider cone, similar to how the nozzle on a garden hose focuses water into a tight stream instead of letting it spray everywhere. When a gamma-ray burst jet points directly at Earth, we observe what's called a blazar effect, where the light appears to brighten and fade as the beam sweeps past our line of sight, like a cosmic lighthouse. And these blazars can vary in brightness by factors of hundreds within just days, or even hours, as turbulence in the jet creates bright knots of emission that travel toward us at apparent speeds that can exceed the speed of light due to projection effects. Though nothing is actually moving faster than light, in reality, this faster-than-light motion is an illusion created by the geometry of the situation, because when something is moving at 99% of the speed of light almost directly toward you, it appears to cover vast distances in impossibly short times from your perspective, even though the actual motion respects the cosmic speed limit perfectly. The particles within gamma-ray burst jets carry energies that are millions of times greater than anything we can create in our most sophisticated particle accelerators, like the Large Hadron Collider, with individual protons racing along the jet at speeds so close to light speed that their relativistic mass increases by factors of thousands, essentially turning ordinary matter into cosmic bullets of incredible destructive potential. These ultra-high energy particles interact with magnetic fields in the jet and with photons from the surrounding environment, creating cascades of secondary particles and electromagnetic radiation through processes like synchrotron emission and inverse Compton scattering, where low-energy photons get boosted up to gamma-ray energies by colliding with the ultra-relativistic electrons in the jet. The total energy budget of a gamma-ray burst is so enormous that it can rival or even exceed the total energy released by all the stars in an entire galaxy over millions of years, all concentrated into an event lasting anywhere from a few milliseconds to several hundred seconds. And this makes gamma-ray bursts not just the brightest explosions in the universe, but also the most energetically efficient at converting matter and gravitational potential energy into pure electromagnetic radiation. Scientists estimate that some gamma-ray bursts may convert as much as 50% or more of the available energy into gamma rays, which is an absolutely remarkable efficiency compared to most astrophysical processes, where only a tiny fraction of the total energy ends up being radiated away as light. The shock waves created by gamma-ray burst jets don't stop when they leave the star, because they continue propagating outward into the surrounding interstellar medium, plowing through clouds of gas and dust and heating them to temperatures of millions or even billions of degrees, creating what astronomers call the afterglow that can persist for weeks or months after the initial burst and can be observed across the electromagnetic spectrum from radio waves all the way up to X-rays. This afterglow emission comes from the forward shock created as the jet material slams into the environment around the dead star, as well as from a reverse shock that propagates backward into the jet material itself. And by studying how the afterglow evolves over time, scientists can learn about the properties of the jet, the energy of the explosion, and the density of the surrounding medium through which the blast wave is propagating. Gamma-ray bursts are so powerful, they can actually affect their environments on galactic scales, with the most intense bursts capable of heating entire regions of intergalactic gas, disrupting star formation across volumes spanning millions of light years, and potentially sterilizing any planets that happen to be too close to the explosion by bathing them in lethal doses of gamma-ray radiation that would destroy the ozone layer and expose the surface to harmful ultraviolet light from the star. If a gamma-ray burst occurred within our own Milky Way galaxy and happened to point its jet directly at Earth, the consequences could be catastrophic for life on our planet, potentially causing a mass extinction event by stripping away the ozone layer and irradiating the surface. And some scientists have speculated that the late Ordovician mass extinction that occurred about 445 million years ago might have been triggered by a relatively nearby gamma-ray burst, though this hypothesis remains controversial and difficult to prove. Fortunately for us, gamma-ray bursts are incredibly rare events, even on cosmic timescales, occurring only a few times per galaxy per million years, and the probability of one happening close enough and being oriented correctly to threaten Earth is vanishingly small, so we can observe these incredible explosions without worrying too much about being caught in their destructive path. The study of gamma-ray bursts has revealed that they come in at least two distinct varieties based on their duration, with long-duration bursts lasting anywhere from 2 seconds to several hundred seconds, and being associated with the deaths of massive stars and core collapse supernovae, while short-duration bursts last less than 2 seconds and appear to be created by the merger of two neutron stars, or a neutron star, and a black hole, which creates a different type of explosion but still produces jets and gamma rays through similar mechanisms. These short bursts are particularly interesting because they're also the sources of gravitational waves that can be detected by observatories like LIGO and Virgo. And in 2017, scientists made the historic first simultaneous observation of both gravitational waves and electromagnetic radiation from a single event, a neutron star merger that produced both ripples in space-time and a gamma-ray burst along with a longer-lived optical transient called a kilonova. The jets from gamma-ray bursts also serve as incredible cosmic laboratories for testing our understanding of physics under extreme conditions that can never be replicated on Earth, because in these jets matter is accelerated to energies and densities where quantum mechanics, general relativity, and particle physics all become important simultaneously, creating a regime where new phenomena might emerge, and our current theories might break down or reveal new insights. Recent observations have revealed gamma-ray bursts at increasingly large distances, with some events detected from when the universe was less than 10% of its current age. And these ancient bursts help us understand how the first generations of stars formed, lived, and died, while also serving as bright beacons that illuminate the intervening matter between us and the burst, allowing astronomers to study the evolution of galaxies and the intergalactic medium across cosmic history. The sheer power and brightness of gamma-ray bursts make them visible across the entire observable universe, which means they can potentially serve as standardizable candles for measuring cosmic distances and studying the expansion history of the universe, complementing other methods like Type Ia supernovae, and providing independent checks on our understanding of dark energy and the overall geometry of space-time. But even with all their incredible power, gamma-ray bursts are not the absolute limit of what the universe can produce, because there are other phenomena that approach or potentially exceed their energy output, though few, if any, can match the concentrated brilliance and the focused destructive potential of a gamma-ray burst jet pointed directly at an observer across billions of light-years of space. At the heart of our Milky Way galaxy, hiding behind thick clouds of dust and gas, some 26,000 light-years from where you're sitting right now, sits a gravitational monster that weighs in at approximately 4 million times the mass of our Sun. And this beast, known as Sagittarius, a star devours everything that ventures too close, from massive clouds of interstellar gas to entire star systems that made the fatal mistake of wandering into its gravitational sphere of influence. This black hole, at our galaxy's center, might sound impossibly massive and terrifyingly powerful, and it absolutely is compared to anything we encounter in everyday life. But here's the truly mind-blowing part. Sagittarius, a star, is actually considered small, almost tiny really, when compared to the true titans that lurk in the hearts of distant galaxies across the cosmic deep. Some supermassive black holes, scattered throughout the universe, contain the mass of 40 billion suns, or even more, all compressed into a region smaller than our entire solar system. And these gravitational leviathans are so massive and so powerful that they fundamentally reshape the galaxies that host them, controlling star formation across hundreds of thousands of light years and determining the fate of billions upon billions of stars. These objects are like cosmic vacuum cleaners, operating on a scale that defies comprehension, with gravity so overwhelmingly intense that nothing, not even light itself, traveling at 300,000 kilometers per second, can escape once it crosses the point of no return, called the event horizon. The gravity around these supermassive black holes is so strong that it literally bends space and time into impossible geometries, creating distortions in the fabric of reality that would seem like pure science fiction if we didn't observe them directly through our telescopes and gravitational wave detectors. Space curves around them like water swirling down a cosmic drain, and time itself slows down near the event horizon, meaning that if you could somehow survive close to a supermassive black hole and watch someone falling in from a safe distance, you would see them appear to freeze in time, moving slower and slower as they approach the horizon until they seem to stop completely, even though from their perspective, they would cross the horizon in finite time. These gravitational monsters didn't grow slowly through gentle accumulation over cosmic timescales, at least not all of them, because astronomers have discovered quasars shining from the early universe when the cosmos was less than 1 billion years old. And these quasars are powered by black holes that somehow grew to contain billions of solar masses in what amounts to the cosmic equivalent of just a few minutes after the Big Bang. This creates one of the most profound mysteries in modern astrophysics, because normal stellar evolution simply cannot explain their existence, as there hasn't been enough time in the history of the universe for these black holes to have grown so large through the slow process of accreting matter, one star at a time. The leading theory attempting to explain these impossibly massive early black holes suggests they began as huge seeds formed directly from collapsing clouds of primordial gas in the first few 100 million years after the Big Bang. And unlike stellar mass black holes that form from dying stars and start with maybe 10 or 20 solar masses, these primordial monsters may have been born with hundreds of thousands or even millions of solar masses right from the moment of their creation. This enormous head start would have allowed them to grow rapidly by consuming the dense clouds of hydrogen gas that filled the early universe, and by merging with other black holes during the frequent galaxy collisions that characterized the chaotic young cosmos. They could have reached billions of solar masses while the universe was still in its infancy. When material spirals into a supermassive black hole, friction between the layers of infalling gas and dust heats everything up to temperatures that can exceed millions or even billions of degrees. And this creates what astronomers call an accretion disk, a swirling vortex of superheated matter that glows brighter than 100 billion stars combined. The disk rotates so rapidly that material near the inner edge, just outside the event horizon, travels at significant fractions of the speed of light while completing orbits around the black hole multiple times per second. And at these extreme velocities, relativistic effects become impossible to ignore as time dilation stretches seconds into hours for outside observers, and the energy of individual particles gets boosted to levels that dwarf anything achievable in our terrestrial laboratories. The most luminous quasars, which are just supermassive black holes, actively feeding on huge quantities of matter, can be detected from literally across the entire observable universe, shining like cosmic lighthouses that broadcast their presence across distances of billions upon billions of light years. These brilliant beacons outshine their entire host galaxies by enormous factors, making the combined light of hundreds of billions of normal stars seem pathetically dim by comparison. And this happens because the accretion disk around the black hole converts matter into energy with an efficiency that makes nuclear fusion look wasteful, transforming anywhere from about 6% to potentially 32% of infalling matter's mass directly into pure electromagnetic radiation, according to Einstein's famous equation relating mass and energy. Compare that to the fusion reactions happening in stars like our Sun, which convert only about 0.7% of the hydrogen's mass into energy. And you can see why quasars powered by black holes are so incredibly bright, despite being relatively small objects compared to entire galaxies. The most violent and active supermassive black holes don't just pull matter in, they also launch jets of particles outward from their poles at speeds approaching 99.9% of the speed of light, creating cosmic fire hoses that stretch for hundreds of thousands or even millions of light years across the universe, while maintaining such perfect focus that they appear as thin lines even when observed from billions of light years away. These jets carry enough energy to power 1 trillion stars simultaneously, and they're created through a complex interplay of the black hole's rotation, the magnetic fields threading through the accretion disk, and the extreme physics that occurs when matter and energy interact in the most intense gravitational fields that nature can produce outside of the Big Bang itself. The magnetic fields around, actively feeding black holes, get twisted and amplified by the disk's rotation until they reach strengths that would be considered impossible in any laboratory setting. And these fields channel some of the infalling material away from the black hole's equator and accelerate it to relativistic speeds along the rotation axis, creating two narrow beams that shoot out in opposite directions, perpendicular to the accretion disk. When these jets slam into the surrounding intergalactic medium, they create enormous bubbles of superheated gas that can span hundreds of thousands of light years and persist for hundreds of millions of years. And these bubbles carry so much energy that they can heat entire galaxy clusters, preventing gas from cooling and condensing into new stars across vast regions of space. The feedback from supermassive black holes through these jets and through the radiation pressure from their brilliant accretion disks is now recognized as one of the most important processes regulating galaxy evolution, because without this feedback mechanism shutting down star formation in massive galaxies, theoretical models predict that the biggest galaxies should contain far more stars than we actually observe. Recent observations using instruments like the Event Horizon Telescope, which linked radio telescopes across the entire Earth to create a virtual telescope the size of our planet, have revealed the shadow of supermassive black holes against the glowing backdrop of their accretion disks, providing the most direct visual evidence yet that these objects exist, exactly as Einstein's general relativity predicts they should. The image of the black hole at the center of the galaxy, Messier 87, which contains about 6.5 billion solar masses, showed a dark circular region surrounded by a bright ring of emission. And this is exactly what you would expect to see if light from the accretion disk gets bent around the black hole's intense gravitational field, while light heading too close to the event horizon gets captured and disappears forever. These observations have revealed that supermassive black holes are spinning at significant fractions of the maximum possible rotation rate, with some black holes rotating so fast that their event horizons are dragged around by the spinning spacetime itself in a phenomenon called frame dragging, where the black hole's rotation literally pulls space and time along with it, like honey being stirred in a jar. The relationship between supermassive black holes and their host galaxies is one of the most intriguing discoveries in modern astronomy, because it turns out that the mass of the central black hole is tightly correlated with properties of the galaxy's central bulge, specifically the velocity dispersion of stars in that bulge. And this correlation suggests that black holes and galaxies somehow evolved together through cosmic history in a coordinated dance, where each influenced the other's growth. Galaxies with more massive bulges contain more massive black holes, following a remarkably tight relationship that holds across galaxies, ranging from small dwarf galaxies to giant ellipticals. And this can't be a coincidence, because the black hole represents only about 0.1% of the bulge's mass. Yet somehow the two are connected through processes we're still working to fully understand. The most popular explanation involves feedback, where the black hole's energy output during its active quasar phase heats or expels gas from the galaxy, shutting down both star formation and further black hole growth simultaneously. And this mutual regulation would naturally create a correlation between black hole mass and galaxy properties, even though the black hole itself is tiny compared to the galaxy. Some of the most distant quasars ever detected are so far away that their light has been traveling through space for over 13 billion years, meaning we're seeing these objects as they appeared when the universe was less than 1 billion years old. And incredibly, these ancient quasars appeared just as powerful as nearby ones, indicating that supermassive black holes grew to enormous sizes very quickly after the Big Bang, through processes that may have been different from the relatively sedate growth we see in the modern universe. The mystery of how these early black holes achieved such impossible growth rates has only deepened with recent observations from the James Webb Space Telescope, which has discovered even more distant quasars and found that many of these early supermassive black holes appear to be more massive relative to their host galaxies than we see in the nearby universe, breaking the normal scaling relationships and suggesting that black hole growth outpaced galaxy growth during the universe's first billion years. These observations have forced astronomers to reconsider theories about how the first black holes formed, with some scientists proposing that the seeds of supermassive black holes might have been created directly through the collapse of enormous gas clouds in the early universe, producing black holes containing hundreds of thousands of solar masses right from birth, without going through the normal stellar evolution pathway. Other theories suggest that dense clusters of the very first stars might have merged together to create intermediate mass black holes that served as the seeds for later supermassive black holes, or that unusual physical conditions in the early universe might have allowed black holes to grow faster than the normal Eddington limit, which is the theoretical maximum rate at which a black hole can accrete matter without the radiation pressure from the accretion disk blowing away incoming material. Recent studies have found evidence that some early quasars may indeed have been accreting matter at rates exceeding the Eddington limit in what's called super Eddington accretion, where the black hole grows so rapidly that it violates what we thought were fundamental physical constraints. And this discovery comes from analyzing the X-ray emissions from distant quasars and finding correlations between the temperature of the corona, the hottest region near the black hole, and the speed of winds being driven away from the accretion disk. Quasars with lower energy X-ray emissions, indicating cooler coronas, show faster winds reaching thousands of kilometers per second. And this combination is the signature of super Eddington accretion, where the black hole is feeding so voraciously that it's growing faster than should be possible under normal circumstances. The jets launched by supermassive black holes can remain active for millions or even tens of millions of years, continuously pumping energy into their surroundings. And during this time, they can completely reshape the environment around their host galaxy, creating vast radio lobes that extend far beyond the visible galaxy and can span distances exceeding 1 million light-years from end to end. These radio lobes are filled with ultra-high energy particles spiraling around magnetic field lines and emitting radio waves through synchrotron radiation. and they represent some of the largest structures created by individual objects in the entire universe, dwarfing even giant elliptical galaxies that contain trillions of stars. When astronomers look at these powerful radio galaxies and quasars, they're essentially seeing supermassive black holes at their most active and most violent during brief periods, cosmically speaking, when they have access to abundant fuel in the form of gas and dust. And these active phases may have been much more common in the early universe, when galaxies were still forming, and galaxy mergers were frequent events that could funnel gas towards central black holes. The accretion disks around supermassive black holes are not smooth and uniform, but rather turbulent and chaotic, with magnetic fields creating instabilities that cause the disk to vary in brightness on timescales ranging from minutes to years. And by studying this variability, astronomers can learn about the physical size of the emitting region and the properties of the black hole, including its mass and spin. Modern machine learning techniques are now being applied to analyze the light curves from thousands of quasars simultaneously, searching for patterns that reveal the underlying physics of black hole accretion, and helping to identify unusual objects like binary supermassive black holes, where two massive black holes orbit each other in the aftermath of a galaxy merger. These binary black holes are particularly interesting because when they eventually spiral together and merge, they should produce gravitational waves with wavelengths of light years, far too long for ground-based detectors like LIGO to observe, but potentially detectable using pulsar timing arrays that monitor the incredibly precise rotation rates of millisecond pulsars scattered across the galaxy. The eventual merger of two supermassive black holes would be one of the most energetic events possible in the universe, converting several percent of the total mass into gravitational wave energy and producing ripples in spacetime that could be detected across cosmic distances. And finding these events would open a new window onto how galaxies and their central black holes evolved together throughout cosmic history. Despite all their power and all their influence over galactic evolution, supermassive black holes eventually run out of fuel when they've consumed or expelled all the nearby gas. And when this happens, the brilliant quasar shuts down, and the black hole enters a dormant phase where it sits quietly at the galaxy's center, essentially invisible, except for its gravitational effects on nearby stars. Our own galaxy's central black hole, Sagittarius, a star, is in this dormant state right now, accreting matter at such a low rate that it's millions of times fainter than it could be if it had access to more fuel. And the same is true for most supermassive black holes in the nearby universe, which are essentially sleeping giants, waiting for the next galaxy merger or other event to provide them with fresh supplies of gas to consume. When you look at the most powerful supermassive black holes and quasars in the universe, you're witnessing gravity taken to its absolute extreme, where space-time itself becomes so warped that the normal rules of physics start to break down, and quantum effects might become important, even on scales far larger than atoms. And yet even these titanic objects with masses billions of times that of our sun pale in comparison to forces operating on even larger scales that shape the fate of the entire cosmos. Across 13.8 billion light-years of cosmic space, stretching from one edge of the observable universe to the other, an invisible force is winning a war that's been raging since the Big Bang, and this mysterious power is pushing galaxies farther and farther apart with each passing second, stretching the very fabric of space-time itself like an infinite balloon being inflated by an unseen breath that never stops blowing. Scientists call this force dark energy, and it makes up approximately 70% of everything that exists in the entire cosmos, which means that the vast majority of our universe consists of something we know almost nothing about and have never directly observed or measured in any laboratory. Yet, despite our ignorance about what dark energy actually is, we can see its effects with absolute clarity when we look at the large-scale structure of the universe and measure how fast distant galaxies are moving away from us. Dark energy is fundamentally different from every other force or substance we've encountered, because it doesn't weaken with distance, like gravity or electromagnetism, and instead, as space itself expands and grows larger, more dark energy appears to fill the newly created volume, which means the bigger the universe becomes, the faster it expands in an accelerating feedback loop that seems to violate our intuitions about how forces should behave. It's like a cosmic gas pedal that only knows how to push down harder and harder, growing stronger and more dominant as it pulls everything apart with increasing velocity. And there's no brake pedal anywhere to be found that could slow this acceleration down or reverse it. Scientists discovered this force completely by accident in the late 1990s while studying distant Type Ia supernovae, which are exploding white dwarf stars that serve as excellent cosmic distance markers because they all shine with nearly identical brightness at their peak. And by measuring how bright these supernovae appeared compared to how bright they should be based on their distance calculated from redshift, astronomers expected to find that the universe's expansion was slowing down due to the gravitational pull of all the matter within it, pulling everything back together. Instead, they found exactly the opposite of what they were looking for, discovering that space is actually expanding faster today than it was billions of years ago, as if some invisible hand with unlimited power is pulling everything apart with increasing strength, rather than letting gravity's attractive force slow the expansion, as every cosmologist had assumed would happen. Think of the universe as a gigantic balloon being inflated by an invisible breath that you can't see, hear, or touch. And dark energy is that mysterious breath causing every point on the balloon's surface to move away from every other point at an accelerating rate, while galaxies ride this expanding space like boats on a swelling ocean that's growing larger and larger, completely powerless to resist the tide that carries them into the cosmic deep. The amount of dark energy in the universe appears to increase as space expands, which seems to violate one of the most fundamental laws of physics, called the conservation of energy, that states energy cannot be created or destroyed, only transformed from one form to another. Yet observations consistently show that the energy density of dark energy, meaning the amount of dark energy per unit volume, remains essentially constant even as the total volume of space grows larger and larger with cosmic expansion. Where this extra energy comes from and why it doesn't dilute like ordinary matter and radiation do, when space expands, remains completely unknown and represents one of the deepest mysteries in all of physics. Because if you double the volume of a box containing gas molecules, the density of those molecules drops by half. But if you double the volume of a box containing dark energy, somehow more dark energy appears to maintain the same density as before. Current theories attempting to explain dark energy fall into several broad categories, with the leading candidate being something called the cosmological constant, which is a property of space itself that Albert Einstein originally proposed in 1917 when he was trying to create a static universe model that neither expanded nor contracted, and he later called this addition to his equations his greatest blunder, after Edwin Hubble discovered that the universe actually is expanding. The cosmological constant represents a kind of vacuum energy where empty space itself possesses an intrinsic energy density that doesn't change as space expands. And according to quantum field theory, the vacuum isn't actually empty, but rather filled with virtual particles that pop into and out of existence constantly. And these quantum fluctuations should contribute to the energy of empty space in a way that could manifest as dark energy. However, when physicists try to calculate how much vacuum energy quantum mechanics predicts, they get an answer that's larger than the observed dark energy by a factor of 10 to the power of 120, which is literally the worst prediction in the history of physics, off by 120 orders of magnitude. And nobody knows why the actual value is so incredibly tiny compared to what theory suggests it should be. Another possibility is that dark energy isn't constant, but rather changes over time through something called quintessence, which is a hypothetical dynamic field that varies in strength across different epochs of cosmic history. And if this is correct, then the acceleration of the universe's expansion might increase or decrease in the future, depending on how the quintessence field evolves. Some scientists think dark energy could be evidence that our understanding of gravity needs major revision on cosmic scales, and perhaps Einstein's general relativity breaks down when applied to the entire universe, requiring modifications that would naturally produce the observed acceleration without invoking any mysterious new form of energy. The consequences of dark energy are profound and frankly terrifying when you think about them carefully, because in the far future, perhaps hundreds of billions of years from now, dark energy will tear apart everything we can see today if its properties remain constant and the acceleration continues indefinitely. First, galaxy clusters will be pulled apart as the space between them expands faster than their mutual gravity can hold them together. And these once majestic groupings of thousands of galaxies will separate beyond recognition, becoming isolated islands in an ocean of expanding darkness, where each galaxy can no longer see any of its former neighbors because they've moved beyond the cosmic horizon. Then, as dark energy continues to dominate and grow even more powerful relative to everything else, individual galaxies will begin to lose their ability to hold themselves together against the cosmic expansion, and the space between stars within a single galaxy will start expanding faster than the star's mutual gravitational attraction can compensate for, ultimately dissolving even tightly bound structures like our Milky Way into scattered collections of isolated stars, drifting alone through the void. Eventually, if dark energy continues to grow in strength, or if it transitions to an even more powerful form called phantom energy, the universe could experience something called the Big Rip, where even atoms themselves get stretched apart as the space between atomic nuclei and electrons expands faster than electromagnetic forces can keep them bound together. And in this nightmare scenario, every structure in the universe, from galaxy superclusters down to individual molecules, would be torn to shreds by the accelerating expansion of space itself. Stars will be extinguished one by one as they burn through their nuclear fuel and die, and no new stars will be able to form because the gas needed for star formation will be too spread out and too hot from dark energy's influence to collapse under gravity and ignite fusion reactions. Planets will drift away from their parent stars as the orbits gradually decay and space expansion becomes significant even on solar system scales. And eventually even the fundamental particles that make up matter might be separated by vast distances as space continues its relentless expansion, driven by dark energy's repulsive gravity. Dark energy, which seems relatively gentle and barely noticeable today when we measure the expansion rate of the universe, will become the cosmos's final destroyer in this scenario, methodically unmaking everything that gravity and the other fundamental forces worked billions of years to create, leaving behind a dark, cold, empty universe with no structures, no complexity, and no possibility for life or consciousness to exist anywhere. The current density of dark energy is astonishingly low, roughly 6 times 10 to the negative 10 joules per cubic meter, which is far less than the density of ordinary matter or dark matter within galaxies. But despite this incredibly low density, dark energy dominates the universe's total mass energy content because it's spread uniformly across all of space, while matter is clumped into galaxies and galaxy clusters with vast empty regions in between. When cosmologists calculate the energy budget of the universe, they find that dark energy contributes about 68 to 70% of the total. Dark matter makes up about 27%, and ordinary matter, the atoms and molecules that make up everything we can see and touch, accounts for only about 5% of the total. which means that 95% of the universe consists of substances we don't understand and can't directly observe, except through their gravitational effects or their influence on cosmic expansion. The evidence for dark energy doesn't come from a single observation, but rather from multiple independent lines of evidence that all point to the same conclusion, including the brightness and redshift relationships of distant supernovae, the pattern of temperature fluctuations in the cosmic microwave background radiation left over from the Big Bang, the large-scale distribution of galaxies across billions of light years, and the way that light from distant galaxies gets bent and distorted by gravitational lensing as it passes through the universe's web-like structure. All of these different observations can only be explained consistently if the universe contains a dominant component with negative pressure that causes space to accelerate in its expansion. And the agreement between these independent measurements gives scientists confidence that dark energy really exists, even though we don't know what it is. One of the most puzzling aspects of dark energy is the coincidence problem, which asks why dark energy happens to have roughly the same density as matter in the present epoch of cosmic history, because if dark energy were much stronger, it would have dominated much earlier and prevented galaxies from forming at all, while if it were much weaker, we wouldn't notice its effects yet, and the universe would still be in a matter-dominated phase. The fact that we happen to live at the precise moment in cosmic history when dark energy and matter have comparable densities seems like an unlikely coincidence that might hint at some deeper connection between them that we don't yet understand. Some scientists invoke the anthropic principle to explain this coincidence, arguing that we necessarily find ourselves in an epoch where galaxies can form and intelligent life can evolve. Because in universes, or epochs, where dark energy dominates too early, no observers would exist to wonder about the question. But this explanation is unsatisfying to many physicists who prefer to find fundamental physical reasons rather than selection effects based on our existence. The discovery of dark energy has forced cosmologists to confront the possibility that we might be living in a multiverse, an ensemble of many universes with different physical properties and different amounts of dark energy. And if this is true, then our universe's particular value of dark energy might just be a random draw from a vast landscape of possibilities, rather than being determined by any fundamental physical principle. Recent missions and experiments designed to study dark energy include the Dark Energy Survey, which mapped hundreds of millions of galaxies to trace the growth of cosmic structure over time, the Planck satellite, which measured the cosmic microwave background with unprecedented precision, and upcoming projects like the Vera Rubin Observatory, which will observe billions of galaxies, and the Euclid Space Telescope, which launched in 2023 to map the geometry of the universe and constrain dark energy's properties. These experiments aim to determine whether dark energy is truly constant across time and space, like a cosmological constant, or whether it varies in ways that would point toward quintessence or other more exotic explanations. And they will measure the equation of state parameter for dark energy, which quantifies the relationship between its pressure and energy density and can distinguish between different theoretical models. If dark energy turns out to be the cosmological constant with an equation of state parameter of exactly -1, then it represents a fundamental property of spacetime itself and suggests that the vacuum of space has an intrinsic energy that will drive cosmic acceleration forever. But if the equation of state parameter differs from -1 or changes over time, that would indicate something more dynamic is happening and could open the door to new physics beyond our current understanding. The mystery of dark energy connects to some of the deepest questions in theoretical physics, including the nature of the quantum vacuum, the possible existence of extra dimensions beyond the 3 spatial dimensions and one-time dimension we experience, and the ultimate fate of our universe over timescales that dwarf the current age of the cosmos by factors of billions or more. Some theories propose that dark energy could be related to modifications of gravity on the largest scales, where Einstein's general relativity needs to be extended or replaced with a more complete theory that incorporates quantum effects, and these modified gravity theories could potentially explain cosmic acceleration without requiring any new form of energy at all. Other possibilities include the idea that what we interpret as dark energy might actually be an illusion created by the fact that we live in an unusual region of the universe with lower than average density. And from our perspective, it would appear that space is accelerating, even though globally the expansion might be slowing down. But this local void hypothesis has been largely ruled out by observations, showing that the acceleration appears uniform across the entire sky. Dark energy also raises philosophical questions about the long-term future of humanity and any other intelligent civilizations that might exist in the universe. Because if dark energy continues to dominate and the acceleration persists, eventually the observable universe will shrink as more and more galaxies recede beyond the cosmic horizon, where their light can no longer reach us, and future astronomers living trillions of years from now would see only their local group of gravitationally bound galaxies, surrounded by darkness with no evidence that billions of other galaxies once filled the sky. The study of dark energy represents one of the greatest intellectual challenges humanity has ever undertaken, because we're trying to understand the dominant component of the entire universe using only indirect observations and theoretical reasoning. And the answer to what dark energy is could revolutionize our understanding of physics as completely as quantum mechanics, relativity did in the early 20th century. Whether dark energy is vacuum energy, a new field, a modification of gravity, or something entirely different that we haven't even imagined yet, solving this mystery will require new observations from more powerful telescopes and satellites, new theoretical insights that might unify quantum mechanics and gravity, and perhaps revolutionary conceptual breakthroughs that force us to completely rethink our assumptions about space, time, and the nature of physical reality itself. And yet, despite all its power to reshape the cosmos on the largest possible scales, dark energy operates so subtly on smaller scales that you would never notice its effects in your daily life, or even when observing our solar system or galaxy, because its influence only becomes dominant when you look at the universe as a whole across distances of billions of light years, where the cumulative effect of space expansion finally overwhelms the attractive force of gravity that binds smaller structures together. Imagine taking an entire mountain and compressing it down to the size of a single sugar cube sitting on your kitchen counter. And even after squeezing that mountain with impossible force, until it occupies almost no volume at all, the result would still be about 1,000 times less dense than a neutron star, which represents one of the most extreme states of matter that can exist anywhere in the universe without collapsing completely into a black hole. These cosmic lighthouses pack more mass than our entire sun, which contains 99.86% of all the mass in our solar system, into a sphere just 20 to 24 kilometers across, roughly the size of a medium-sized city like Manhattan. And this creates gravitational fields so incredibly intense that they warp light rays into curves and bend space-time itself into geometries that seem impossible until you see the mathematical equations describing them. A neutron star is what remains after a massive star containing 8 to 20 times the sun's mass, runs out of nuclear fuel, and can no longer generate the outward pressure needed to resist gravity's inward crush. And when this happens, the star's iron core, which has spent millions of years building up as the final product of nuclear fusion, suddenly collapses in less than a second, imploding faster than sound can travel, and crushing protons and electrons, together with such tremendous force that they merge into neutrons, while releasing an absolutely staggering flood of ghostly particles called neutrinos that carry away most of the energy from the collapse. The outer layers of the star rebound off this suddenly rigid neutron core and explode outward as a supernova that can briefly outshine an entire galaxy, but the core itself remains behind as a neutron star, spinning rapidly because the conservation of angular momentum amplifies the original star's rotation rate by factors of millions as the core shrinks down to a tiny fraction of its original size, just like how a figure skater spins faster and faster when they pull their arms in close to their body. The density of neutron star material is so extreme that a single teaspoon, if you could somehow scoop it up and bring it back to Earth, would weigh approximately 600 million tons, which is roughly the mass of all the water in all the Great Lakes combined, or about 10,000 times the mass of the Great Pyramid of Giza. And if you drop this teaspoon of neutron star matter, it would instantly plunge through the Earth like a bullet through tissue paper, punching straight through our planet's crust, mantle, and core, before emerging on the other side and oscillating back and forth through the Earth like a pendulum until friction finally brought it to rest at the planet's center. The surface of a neutron star exists in a realm where normal physics breaks down and matter behaves in ways that seem completely alien to our everyday experience, because the gravitational acceleration at the surface reaches about 2 × 10 to the power of 12 meters per second squared, which is roughly 200 billion times stronger than Earth's surface gravity. And this means that if you could somehow stand on a neutron star, you would weigh about the same as Mount Everest weighs on Earth. And even the tiniest movement would require energy equivalent to detonating nuclear weapons. Mountains on neutron stars, if they exist at all, can be at most a few millimeters tall, because anything higher would be crushed flat instantly by the overwhelming gravitational force. And the surface itself is thought to be incredibly smooth, with a solid crust made of atomic nuclei arranged in crystalline lattices that are squeezed so tightly together they form the strongest material in the universe, about 10 billion times stronger than steel. But gravity isn't even the most terrifying feature of neutron stars, because these stellar remnants possess magnetic fields that are typically 1 trillion times stronger than Earth's protective magnetosphere that shields us from harmful solar radiation. And these invisible force fields trap charged particles and accelerate them to speeds approaching the speed of light, while creating beams of electromagnetic radiation that sweep across space like cosmic searchlights, powered by the fundamental forces of the universe. The magnetic field of a typical neutron star is powerful enough that it could erase every credit card on Earth from a distance of about 600,000 kilometers, which is roughly halfway between Earth and the Moon. And if you could somehow approach within 1,000 kilometers of a neutron star, which would be impossible for countless other reasons, the magnetic force would be strong enough to literally pull the iron atoms from your blood and completely disrupt the electromagnetic forces that hold molecules together in your body. These magnetic field lines become visible in a sense as they trap and channel streams of charged particles into narrow beams that emerge from the magnetic poles. And when these magnetized neutron stars rotate, they become pulsars that fire beams of radio waves, X-rays, and gamma rays with the precision of the most accurate atomic clocks ever built by human technology. Some pulsars spin as fast as 716 times per second, which is faster than a kitchen blender and faster than you can even comprehend. Yet they maintain absolutely perfect timing that rivals or exceeds the best time-keeping devices in our laboratories, with some millisecond pulsars showing variations of less than 1 microsecond over years of observation. Each pulse of radiation marks another complete rotation of a stellar corpse spinning in the darkness of space, and by measuring the precise timing of these pulses, astronomers can learn about the neutron star's mass, radius, magnetic field strength, and even detect the presence of planets orbiting the dead star or gravitational waves passing through our region of space. The interior structure of neutron stars is one of the most fascinating puzzles in astrophysics, because as you go deeper from the surface toward the center, you encounter increasingly exotic states of matter that cannot exist anywhere else in the universe and cannot be replicated in any laboratory, no matter how advanced our technology becomes. The outer crust, extending down to densities of about 6 times 10 to the power of 8 kilograms per cubic meter, consists of atomic nuclei embedded in a sea of electrons. But these aren't normal nuclei because they're incredibly neutron-rich, containing far more neutrons than protons compared to stable isotopes found on Earth. And as you descend deeper into the inner crust, where densities reach about 4 times 10 to the power of 11 kilograms per cubic meter, you reach a point called the neutron drip line, where nuclei become so overloaded with neutrons that individual neutrons start to leak out and form a fluid of free neutrons flowing between the nuclei like water seeping through a sieve. Going deeper still into what scientists call the outer core, the density becomes so extreme that individual nuclei dissolve completely, and you have a superfluid mixture of neutrons with maybe 5 to 10% protons and electrons sprinkled in. And this neutron superfluid has zero viscosity, meaning it flows without any resistance whatsoever, which can lead to sudden glitches in pulsar rotation rates when vortices in the superfluid interior suddenly transfer angular momentum to the solid crust. The very center of a neutron star, where densities may exceed 5 times 10 to the power of 17 kilograms per cubic meter, which is several times higher than the density of atomic nuclei themselves, remains a complete mystery because we simply don't know what happens to matter under such incomprehensible pressures, and various theories suggest possibilities ranging from exotic particles called hyperons that contain strange quarks to pion condensates, where the boundary between neutrons and protons becomes blurry, to quark-gluon plasma, where neutrons dissolve into their constituent quarks, and the star's core becomes essentially one giant atomic nucleus made of free quarks. Some neutron stars, called magnetars, take the already extreme magnetic fields of ordinary neutron stars and amplify them by factors of 1,000 or more, creating magnetic field strengths approaching 10 to the power of 15 Gauss, which is close to the theoretical maximum strength that quantum electrodynamics allows before the vacuum of space itself starts behaving in bizarre ways. These magnetars are thought to be powered by the decay of their incredibly strong magnetic fields rather than by rotation like ordinary pulsars, and when their crusts crack and shift in events called starquakes, the sudden rearrangement of the magnetic field releases more energy in 1/10 of a second than our sun produces in 100,000 years. The most powerful magnetar flare ever recorded occurred on December 27, 2004, when a magnetar designated SGR 1806-20 suddenly erupted with a burst of gamma rays and X-rays so intense that it temporarily saturated detectors on satellites across the solar system and measurably affected Earth's upper atmosphere from a distance of 50,000 light-years, which is halfway across our galaxy. If this magnetar had been located just 10 light-years from Earth, instead of 50,000, the radiation from its giant flare would have caused a mass extinction event on our planet by destroying the ozone layer and bathing the surface in lethal doses of gamma rays. And even at its actual distance, the flare released as much energy in its initial spike, lasting 2/10 of a second, as the sun emits in 150,000 years. The magnetic field around a magnetar is so intense that it affects the very structure of empty space itself, causing the quantum vacuum to become birefringent, like a crystal, which means that light waves passing through this magnetized void get split into two components with different polarizations that travel at slightly different speeds. And this effect has been directly observed in the X-ray emissions from several magnetars, providing experimental confirmation of quantum electrodynamics predictions about how electromagnetic fields should behave at these extreme strengths. Any ordinary matter that falls onto a neutron star's surface, whether it's gas from a companion star or debris from an asteroid, would be compressed instantly into a layer just a few millimeters thick, despite whatever thickness it had before impact. and the kinetic energy of this infalling matter gets converted to heat so efficiently that the impact generates temperatures of millions or billions of degrees and releases more energy than thermonuclear weapons. A marshmallow dropped from waist height onto a neutron star's surface would hit with the kinetic energy of an atomic bomb, releasing approximately the same amount of explosive power as the weapon that destroyed Hiroshima. And this happens because the escape velocity from a neutron star is about 1/3 to 1/2 the speed of light, which means anything falling toward the surface gets accelerated to a significant fraction of light speed before impact. Neutron stars can exist in binary systems where they orbit another star, and when their companion is a normal star that has expanded into a red giant, gas from the outer layers of the companion can flow toward the neutron star and form an accretion disk, similar to what happens around black holes. And as this gas spirals inward and gets heated by friction, it emits intense X-rays that make these systems some of the brightest X-ray sources in the galaxy. The gas flowing onto the neutron star's surface can build up in a layer of hydrogen and helium that gradually gets compressed and heated by the star's intense gravity. And when enough material accumulates, the entire layer suddenly ignites in a runaway thermonuclear explosion called an X-ray burst that releases as much energy in a few seconds as the sun emits in a week, causing the neutron star to brighten by factors of 10,000 to 100,000 before fading back to its normal luminosity over the course of minutes. Some neutron stars in binary systems can have their rotation rates increased dramatically through a process called accretion-induced spin-up, where the angular momentum carried by infalling material from the companion star gradually spins the neutron star faster and faster over millions of years until it's rotating hundreds of times per second. And these millisecond pulsars represent some of the most stable clocks in the universe, with timing precision that in some cases exceeds our best atomic clocks. The study of neutron stars provides unique insights into fundamental physics because these objects create natural laboratories where matter is compressed to nuclear densities. Gravitational fields approach the theoretical maximum possible for non-black hole objects. Magnetic fields reach strengths that dwarf anything achievable on Earth, and temperatures range from billions of degrees in the atmosphere down to possibly the coldest matter in the universe, in the superfluid core, all within a sphere about the size of a city. When two neutron stars spiral together and merge in a violent collision, they create not only gravitational waves that ripple through space-time, but also a kilonova explosion that forges heavy elements like gold, platinum, uranium, and other elements beyond iron through rapid neutron capture. And the 2017 observation of both gravitational waves and electromagnetic radiation from a neutron star merger marked the beginning of multi-messenger astronomy, where we can study cosmic events using multiple independent channels of information. The equation of state for matter inside neutron stars, which describes how pressure relates to density at nuclear densities and beyond, remains one of the biggest unsolved problems in physics, because we can't recreate these conditions in laboratories, and our theoretical understanding of the strong nuclear force becomes uncertain at such extreme densities. So astronomers try to constrain the equation of state by precisely measuring neutron star masses and radii. With recent observations from instruments like NASA's NICER mission aboard the International Space Station, providing the most accurate measurements yet, some neutron stars show X-ray emission that pulsates not at the rotation frequency, but at frequencies of several hundred hertz. And these oscillations during X-ray bursts are thought to arise from waves traveling around the star's surface, or from hot spots rotating into and out of view. And by analyzing these oscillations, scientists can potentially determine the neutron star's radius and test different theoretical models of the equation of state. The maximum possible mass for a neutron star, beyond which even neutron degeneracy pressure cannot prevent collapse into a black hole, is somewhere between 2 and 3 solar masses, based on observations and theoretical calculations. with the exact value depending on the equation of state, and finding the heaviest possible neutron star or the lightest possible black hole would provide crucial information about where this dividing line lies and what happens to matter at the very limit of density before spacetime itself gives way and an event horizon forms. Yet, despite all their incredible power, despite magnetic fields that could rip atoms apart and gravity that warps spacetime into pretzels and densities that crush matter into exotic forms that exist nowhere else, neutron stars and magnetars operate on relatively small scales, measuring just tens of kilometers across, and to find phenomena that rival or exceed their power, we need to look beyond even these extreme objects to forces and events that operate on vastly larger scales. Beyond everything we've discussed so far, beyond the incredible power of neutron stars and the mind-bending density of supermassive black holes, lurk theoretical phenomena that push physics to its absolute breaking point and might represent forces so powerful they could literally destroy the universe or reshape reality itself in ways that make every other cosmic event look like a gentle breeze, stretching across the observable universe and possibly far beyond are invisible threads that could slice through entire planets like wire through cheese. And these cosmic superstrings, if they actually exist, are one-dimensional objects thinner than a proton, yet potentially longer than entire galaxy clusters, representing scars left over from the birth of the universe itself, when space-time underwent violent phase transitions in the first inconceivably brief moments after the Big Bang. According to string theory and related frameworks in theoretical physics, cosmic strings formed during the first fraction of a second after creation, when the universe was incredibly hot and dense and underwent rapid changes in its fundamental properties, and they're like cracks in a frozen pond marking the boundaries where different regions of space crystallized in slightly different ways as the cosmos cooled from its initial state of perfect symmetry, where all forces were unified into one. A cosmic string, just 1 meter long, would weigh as much as the entire Earth, despite being so thin that it's essentially one-dimensional, having length but no meaningful width or height in the conventional sense. And these objects exist at the very boundary between existence and nothingness, between matter and energy, between reality and pure mathematics made manifest in physical form. The energy contained within even a short segment of cosmic string is almost incomprehensible, because a string spanning the distance from Earth to the Moon, which is about 384,000 kilometers, would contain enough mass energy to power human civilization for trillions upon trillions of years at our current consumption rates. Yet this enormous energy would be concentrated in a line so impossibly thin that it has no measurable thickness, even in principle, making cosmic strings the ultimate expression of energy density anywhere in the universe. If cosmic strings move through space, and they probably do at speeds that could approach the speed of light, they would create ripples in space-time itself by generating gravitational waves with a unique signature that's completely different from those produced by black hole mergers or neutron star collisions. And if we could detect these waves using our increasingly sensitive gravitational wave observatories, it would provide the first direct evidence that cosmic strings actually exist rather than being merely mathematical curiosities. When two cosmic strings intersect each other while whipping through space, they can reconnect in new configurations and create loops that oscillate like guitar strings being plucked by the hand of the universe itself. But instead of producing sound waves that travel through air, these vibrating cosmic string loops generate distortions in the fabric of reality itself, sending gravitational waves rippling outward at the speed of light and carrying energy away from the loop until it gradually shrinks and eventually disappears in a final burst of space-time distortion. Some scientists have proposed that cosmic strings could act as cosmic highways, enabling faster-than-light travel through folded space, because if 2 points in space were connected by a cosmic string, you could theoretically travel along the string and arrive at your destination before light traveling through normal space, though this remains entirely speculative and might be prevented by quantum effects or other physical constraints we don't yet understand. Even more terrifying than cosmic strings is the possibility of vacuum decay, a theoretical catastrophe that could end everything we know in an instant without any warning whatsoever. And here's why this is so incredibly dangerous. The Higgs field, which permeates all of space and gives particles their mass, might not be in its lowest possible energy state, which means it could be sitting in what physicists call a false vacuum that appears stable, but could potentially drop to its true ground state, like a ball balanced on a hill, suddenly rolling down into a valley. If vacuum decay began anywhere in the observable universe, it would create an expanding sphere of true vacuum, moving outward at exactly the speed of light, and nothing could escape this cosmic wave of destruction, because no information or matter can travel faster than light, which means we would have absolutely no warning of its approach until the very instant it arrived and annihilated everything in its path. Inside the bubble of true vacuum, created by this decay, the fundamental constants of nature would be different from what they are now. Particles might have completely different masses, or might not exist at all. Atoms as we know them could not form, because the strong nuclear force might be weaker or stronger. Chemistry and biology would become impossible, and every structure that exists in our current universe, from galaxy superclusters down to individual molecules, would be obliterated as the laws of physics themselves suddenly changed. The energy difference between the false vacuum state we currently inhabit and the true vacuum state could exceed the rest mass energy of all matter in the universe, which means that vacuum decay would release more energy than you could get by converting every single proton, neutron, and electron in existence into pure radiation, making it potentially the most energetic event possible in physics. Another theoretical extreme that could dwarf everything else is the possibility that our entire universe is just one bubble in an infinite ocean of other universes, collectively forming a multiverse where every possible set of physical laws and constants exists somewhere. And if the multiverse is real, then the total energy and power available across all universes combined would be literally infinite, making it the ultimate expression of cosmic power that puts even the Big Bang of our own universe into perspective as just one tiny event among countless others. Some versions of string theory predict the existence of primordial black holes that formed in the first second after the Big Bang, when quantum fluctuations in the early universe's density created regions so dense they immediately collapsed into black holes, ranging from microscopic sizes smaller than atoms to potentially massive objects containing thousands of solar masses. And these primordial black holes might make up some or all of the dark matter we observe gravitationally but cannot see directly. The collision between two universe-sized domain walls, which are two-dimensional defects in space-time, similar to cosmic strings, but with an extra dimension, could release enough energy to make gamma-ray bursts look like birthday candles, potentially destroying or transforming entire regions of space, spanning billions of light years, and rewriting the laws of physics across vast cosmic volumes. Kugelblitz black holes represent another theoretical extreme, where you concentrate enough electromagnetic radiation, specifically enough photons in a small enough volume, that the pure energy creates a black hole even though you haven't used any matter at all. And this demonstrates that energy and mass are truly equivalent, according to Einstein's famous equation, with a sufficiently powerful laser focused tightly enough, potentially creating a black hole purely from light. The interior of a black hole beyond the event horizon remains the ultimate unknown in physics, because general relativity predicts a singularity where density becomes infinite and space-time curvature becomes infinite, which almost certainly means our theories break down completely at that point. And we need a theory of quantum gravity to understand what really happens at the center of a black hole, but we don't have such a theory yet despite decades of effort from the world's best physicists. Some theories propose that what we call black hole singularities might actually be incredibly dense but finite structures called gravastars or Planck stars, where quantum effects become important and prevent the formation of true mathematical infinities. But these remain speculative ideas without any observational evidence to support or refute them. The Planck scale represents the absolute limit, where quantum effects and gravitational effects become equally important, occurring at energies of about 10 to the power of 19 billion electron volts, and distance scales of about 10 to the power of -35 meters, which is so incredibly tiny that you could fit more Planck lengths into the width of a proton than you could fit protons into the observable universe. And at these scales, space-time itself probably becomes quantized and foamy with constantly fluctuating geometry that bears no resemblance to the smooth continuum we experience in everyday life. White holes are theoretical time-reversed versions of black holes where nothing can enter and everything must eventually leave, representing solutions to Einstein's equations that are mathematically valid but have never been observed and probably don't exist in our universe because they would violate the second law of thermodynamics by decreasing entropy. Though some scientists have speculated that the Big Bang itself might have been a white hole, or that black holes might connect to white holes in other universes through wormholes. Naked singularities, which are singularities without event horizons protecting them from the outside universe, are predicted by some solutions to general relativity, but are prohibited by the cosmic censorship hypothesis, which states that nature always hides singularities behind event horizons. And if naked singularities could exist, they would create regions where all predictions break down, and literally anything could happen, because the laws of physics would cease to be deterministic. The false vacuum decay scenario mentioned earlier could potentially be triggered by high-energy particle collisions in accelerators like the Large Hadron Collider, and before the LHC was turned on, some people worried that it might accidentally destroy the universe by causing vacuum decay, or creating a black hole that would consume Earth. But physicists calculated that cosmic rays hitting Earth's atmosphere regularly produce collisions at energies far exceeding anything achievable in the LHC. And since the universe hasn't been destroyed yet, despite billions of years of cosmic ray bombardment, our particle accelerators are almost certainly safe. Wormholes represent another theoretical structure, where space-time becomes so warped that distant points in the universe get connected by a tunnel or shortcut through higher dimensional space. And, if traversable wormholes could be created and stabilized, which would require exotic matter with negative mass, that probably doesn't exist, they would enable faster-than-light travel, and potentially even time travel into the past, with all the paradoxes that entails. The holographic principle, emerging from studies of black hole thermodynamics, suggests that all the information contained in a volume of space can be encoded on the boundary of that region, which implies that our three-dimensional reality might be a projection from a two-dimensional surface, making the entire universe potentially a hologram, where the fundamental reality exists in fewer dimensions than we perceive. Hawking radiation causes black holes to slowly evaporate over incredibly long timescales by emitting particles through quantum effects near the event horizon. And when you calculate how long it takes for a black hole to evaporate completely, you get numbers like 10 to the power of 100 years for supermassive black holes, which is so long that by the time they finish evaporating, every star in the universe will have died, every galaxy will have dispersed, and the cosmos will be a dark, cold, empty place approaching heat death. The information paradox asks what happens to the information about matter that falls into a black hole when that black hole eventually evaporates through Hawking radiation, because quantum mechanics requires that information cannot be destroyed. Yet it seems impossible for information to escape from inside a black hole, and resolving this paradox has driven decades of research into quantum gravity and the nature of space-time itself, with proposals involving quantum entanglement, wormholes connecting black holes to their radiation, and holographic encoding of information on the event horizon. The firewall paradox is a more recent puzzle, suggesting that the event horizon of an old black hole might be a wall of incredibly high-energy radiation that would incinerate anything trying to cross it, contradicting the equivalence principle, which states that freely falling observers shouldn't notice anything special when crossing the horizon. And this paradox has revealed deep tensions between quantum mechanics, general relativity, and our understanding of entanglement that physicists are still working to resolve. Closed time-like curves are paths through space-time that loop back on themselves temporally, allowing an object to travel into its own past, and these are permitted by general relativity under certain exotic conditions, like rapidly rotating black holes or wormholes, but they create devastating paradoxes, like the grandfather paradox, where you could go back in time and prevent your own birth, suggesting that either closed time-like curves don't exist in our universe, or that some mechanism we don't understand prevents paradoxes from actually occurring. The Big Rip scenario occurs if dark energy grows stronger over time instead of remaining constant, and in this case, the accelerating expansion of the universe would eventually become so powerful that it tears apart galaxy clusters, then galaxies, then solar systems, then planets, then molecules, then atoms, then atomic nuclei, then even individual protons and neutrons, ending with the complete destruction of all structure in the universe. In a finite time, perhaps 50 billion years from now, an alternative fate called heat death, or big freeze, occurs if dark energy remains constant and the universe expands forever while cooling down, eventually reaching a state of maximum entropy where all temperature differences have equilibrated, all stars have burned out, all black holes have evaporated, and nothing interesting can ever happen again because there's no free energy left to drive any processes. The Big Crunch is yet another possible fate where the expansion of the universe eventually reverses and everything collapses back together, crushing all matter and energy into an infinitely dense singularity, similar to the Big Bang, but in reverse. Though current observations suggest dark energy makes this scenario unlikely unless dark energy suddenly changes its behavior in the far future. Yet even with all these theoretical extremes, from cosmic strings that could slice through planets to vacuum decay that could destroy the universe in an instant to multiverses containing infinite energy, none of them have been directly observed, and they remain mathematical possibilities emerging from our best theories pushed to their logical limits, which means the true extremes of nature might be even stranger than anything we've imagined so far. 13.8 billion years ago, everything that exists today, every single atom in your body, every star scattered across the night sky, every galaxy containing hundreds of billions of suns, every planet orbiting those suns, and all the vast empty space stretching between them was compressed into a point smaller than a proton, tinier than an atom, smaller than anything you could possibly see, even with the most powerful microscope ever built. And at that moment of unimaginable density and temperature, the universe, as we know it, simply did not exist yet. This was the Big Bang singularity, and it represents the ultimate expression of cosmic power, the moment when existence itself began, when space and time were created from nothing, when the laws of physics that govern everything, from quantum particles to galaxy clusters, first came into being and started shaping reality according to rules that would remain constant for billions of years to come. At this primordial moment of creation, the temperature was so incredibly high that it becomes almost meaningless to assign it a number, but physicists estimate it exceeded 10 to the power of 32 degrees Kelvin, which is hot enough that not only do atoms and molecules not exist, but even the fundamental particles we think of as elementary, like protons and neutrons, cannot exist because they would be ripped apart instantly into their constituent quarks and gluons. And even those quarks and gluons would be constantly transforming into other particles through interactions so violent and so energetic that matter and antimatter continuously annihilated each other and reformed in an endless dance of creation and destruction. The density at the Big Bang singularity was equally incomprehensible, approaching infinity in the mathematical models we use to describe it, which is precisely why physicists believe that general relativity must break down at this point, and a theory of quantum gravity that we don't yet possess would be needed to accurately describe what was really happening in those first inconceivably brief instants. The laws of physics, as we understand them, completely break down at the singularity, which means that temperature, density, time, and even the concept of before cease to have any conventional meaning, because time itself was created at the Big Bang, and asking what happened before the Big Bang might be like asking what's north of the North Pole, a question that sounds meaningful but actually doesn't make sense within the framework of our physical theories. In the first fraction of a second after the initial moment, smaller than the time it takes light to cross the diameter of a proton, something absolutely extraordinary happened that physicists call cosmic inflation, a period when the universe expanded faster than the speed of light itself, growing from submicroscopic dimensions to macroscopic size in less than 10 to the power of negative 35 seconds. This inflation wasn't like ordinary expansion, where things move through space at high velocities, but rather an expansion of space itself, where every point in the universe was moving away from every other point, as new space was continuously created between them. And because this was the fabric of space-time itself, expanding rather than objects moving through space, it didn't violate Einstein's speed limit that says nothing can travel faster than light through space. During this inflationary epoch, the universe grew in size by a factor of at least 10 to the power of 26, which means if you started with something the size of a proton, after inflation it would be larger than the observable universe today. And some models suggest the expansion factor could have been even more extreme, potentially reaching 10 to the power of 78 or higher. The driving force behind inflation is thought to be a hypothetical field called the inflaton field, which temporarily had an enormous energy density that created a kind of repulsive gravity, and this negative pressure caused space to expand exponentially until the inflaton field decayed and dumped all its energy into creating the particles and radiation that would eventually form all the matter we see today, effectively reheating the universe after the cold expansion of inflation. When inflation ended, the energy of the inflaton field was converted into a hot plasma of particles and radiation through a process called reheating, and this marks the beginning of what's traditionally called the hot Big Bang phase, where the universe was filled with an incredibly dense and hot soup of quarks, gluons, electrons, photons, neutrinos, and potentially other exotic particles, all constantly interacting with each other in thermal equilibrium. As the universe continued to expand and cool after inflation, though now at a much more sedate rate compared to the exponential growth during inflation, the four fundamental forces that govern all of nature began to separate from what was originally a single unified force in the earliest moments. First, at around 10 to the power of negative 43 seconds after the Big Bang, during the Planck epoch, gravity separated from the other three forces when the universe had cooled enough that gravitational interactions could be distinguished from quantum effects, and this represents the earliest moment we can meaningfully discuss with our current theories, since before this point, we would need a complete theory of quantum gravity. Then at approximately 10 to the power of negative 36 seconds, the strong nuclear force separated from the electroweak force in what's called the Q-T transition, because it marks the breakdown of grand unified theories that attempt to unify the strong, weak, and electromagnetic forces, and this phase transition released enormous amounts of energy and might have been what triggered cosmic inflation in the first place. Finally, at around 10 to the power of negative 12 seconds, when the temperature had dropped to about 10 to the power of 15 degrees Kelvin, the electromagnetic force separated from the weak nuclear force in the electroweak phase transition. And at this point, all four fundamental forces that we observe today had taken on their distinct identities and began operating independently according to the specific rules that characterize each force. During the first microsecond after the Big Bang, the universe was so hot that quarks and gluons existed freely in what physicists call a quark-gluon plasma. But as the temperature dropped below a few trillion degrees Kelvin, these quarks and gluons began combining into protons and neutrons in a phase transition called quark confinement. And this represents the formation of the first composite particles that would eventually become the building blocks of atomic nuclei. Between about 1 second and 3 minutes after the Big Bang, when temperatures ranged from about 10 billion degrees down to 1 billion degrees Kelvin, a crucial process called Big Bang nucleosynthesis occurred where protons and neutrons collided and fused together to form the nuclei of the lightest elements, primarily deuterium, which is heavy hydrogen containing 1 proton and 1 neutron, helium-3 and helium-4, and trace amounts of lithium. And the precise ratios of these primordial elements created during nucleosynthesis provide some of the strongest evidence supporting the Big Bang theory, because when we measure the abundances of these elements in old stars and gas clouds that haven't been contaminated by later stellar fusion, we find exactly the ratios predicted by Big Bang nucleosynthesis calculations. For the next 380,000 years after nucleosynthesis, the universe remained opaque to light because it was filled with free electrons that constantly scattered photons, making it impossible for light to travel any significant distance before being absorbed and re-emitted in a random direction. So the universe during this period was like a glowing fog where light was constantly bouncing around but couldn't escape to travel freely through space. Then, when the universe had cooled to about 3,000 degrees Kelvin, roughly the temperature of a light bulb filament, electrons and atomic nuclei finally combined to form the first neutral atoms in a process called recombination, even though that's a misnomer, since these electrons and nuclei had never been combined before. And this event marked a crucial turning point called cosmic dawn, when light was suddenly freed to travel across the universe without constant scattering. The photons released during recombination are still traveling through space today, but they've been stretched by the expansion of the universe from visible and infrared wavelengths to microwave wavelengths, and we detect them as the cosmic microwave background radiation, a faint afterglow of the Big Bang that comes from every direction in the sky, with a nearly uniform temperature of about 2.7 degrees Kelvin above absolute zero. The cosmic microwave background is one of the most important pieces of evidence for the Big Bang theory, and the tiny temperature fluctuations in this radiation, which differ by only about 1 part in 100,000 across the sky, represent the seeds of all structure in the universe, because regions that were slightly denser than average had slightly stronger gravity and gradually attracted more matter, eventually growing into the galaxies, galaxy clusters, and large-scale structures we see today. After recombination, the universe entered what astronomers call the Dark Ages, a period lasting several 100 million years, when there were no stars yet to produce light, just clouds of neutral hydrogen and helium gas, slowly collapsing under gravity's pull into denser and denser clumps that would eventually ignite nuclear fusion and become the first stars. These first stars, formed perhaps 200 million years after the Big Bang, were likely much more massive than typical stars today because they were made purely from primordial hydrogen and helium without any heavier elements. And these heavy elements are crucial for allowing gas clouds to cool efficiently through radiation. So without them, the first star-forming clouds had to be much more massive to collapse under their own gravity. The first stars lived fast and died young, burning through their nuclear fuel in just a few million years, before exploding as supernovae that scattered the first heavy elements like carbon, oxygen, nitrogen, silicon, and iron into space, enriching the surrounding gas and enabling subsequent generations of stars to form with more diverse chemical compositions. Around 400 million years after the Big Bang, galaxies began forming as dark matter halos that had been growing through gravitational collapse, accumulated enough regular matter to trigger intense bursts of star formation. And these early galaxies were typically much smaller and more irregular than the majestic spiral and elliptical galaxies we see in the nearby universe, often merging with each other violently to gradually build up into the larger structures we observe today. The Big Bang theory is supported by multiple independent lines of evidence, beyond just the expansion of the universe that Edwin Hubble first discovered in 1929, including the cosmic microwave background radiation discovered accidentally by Arno Penzias and Robert Wilson in 1965, the abundances of light elements produced during Big Bang nucleosynthesis, matching observations with incredible precision, the age of the oldest stars being consistent with the age of the universe, calculated from expansion rates, and the large-scale distribution of galaxies, forming a cosmic web structure that matches predictions from simulations of structure formation, starting from the tiny density fluctuations imprinted in the cosmic microwave background. One of the most remarkable aspects of the Big Bang and inflation is that all the energy and matter in our observable universe, which contains at least 100 billion galaxies each, with hundreds of billions of stars, plus all the dark matter and dark energy, came from quantum fluctuations in that original tiny volume during the inflationary epoch, essentially proving that the universe can indeed get something from nothing through quantum mechanical processes, though the total energy might sum to zero when you account for both positive energy in matter and radiation and negative gravitational potential energy. The flatness problem, which asks why the universe has almost exactly the critical density needed to be geometrically flat rather than curved, and the horizon problem, which asks why regions of space that have never been in causal contact with each other have nearly identical temperatures and properties, are both elegantly solved by cosmic inflation, because the exponential expansion stretched a tiny region that was in thermal equilibrium to scales far larger than the observable universe, making everything we can see today descend from a region small enough to have been causally connected before inflation. Inflation also provides a natural explanation for why the universe is so large and uniform, while still containing the tiny density fluctuations needed to form structure, because quantum fluctuations in the inflaton field itself got stretched to macroscopic scales during inflation and imprinted the pattern of slightly denser and less dense regions that we observe in the cosmic microwave background, and that seeded all the structure formation that followed. The Big Bang represents not just an explosion in space, but an explosion of space itself, creating time as well as matter and energy, and establishing the fundamental laws of physics that would govern everything from quantum fluctuations to galaxy evolution for billions of years, making it truly the most powerful event in the history of the universe and the ultimate origin of everything we see around us. Yet even this cosmic genesis might not represent the absolute beginning if ideas like eternal inflation or the multiverse are correct, in which case our Big Bang could be just one bubble universe among countless others continuously being created in an infinite inflating space that has no beginning and no end. If everything we've discussed so far, from the incomprehensible power of the Big Bang that created our entire universe, to the mind-bending forces operating inside neutron stars, and the mysterious dark energy tearing space apart, seems impossibly vast and powerful, then prepare yourself for an idea that makes all of it look infinitely small by comparison, because there's a real possibility that our entire observable universe, with its hundreds of billions of galaxies and its 13.8 billion year history, is just one tiny bubble floating in an infinite ocean of other universes that collectively form what physicists call the multiverse. This concept isn't just science fiction dreamed up by creative writers looking for interesting storylines, but rather a serious scientific hypothesis that emerges naturally from several different areas of modern physics, including quantum mechanics, cosmic inflation theory, and string theory. And if the multiverse is real, then the total amount of energy and power available across all universes combined would be literally infinite, making it the ultimate expression of cosmic power that puts even our universe's Big Bang into perspective as just one relatively minor event among countless others occurring continuously throughout existence. The multiverse idea comes in several different flavors or levels, depending on which branch of physics you're looking at. And the first and most straightforward version simply extends what we already know about our own universe to its logical conclusion by pointing out that if space is infinite, which many cosmological models suggest it is, then everything that can possibly happen will happen somewhere, given infinite space and infinite matter. This means that far beyond our observable universe's edge, which is about 93 billion light-years away, in every direction representing the farthest distance light, has had time to travel since the Big Bang. There could be other regions of space where completely different histories have played out, and where different arrangements of matter have led to different galaxies, different stars, different planets, and potentially even exact copies of you living out slightly or dramatically different lives, depending on how far away these parallel regions exist. The math here is actually straightforward, even if the implications are bizarre, because if you have infinite space with matter distributed more or less randomly throughout it, then every possible configuration of particles within a given volume, including the exact configuration that makes up you and your entire observable surroundings, must occur infinitely many times, simply because infinity is so incomprehensibly large that it contains every possibility. The second type of multiverse emerges from eternal inflation theory, which extends the cosmic inflation we discussed earlier by suggesting that while inflation ended in our region of space and allowed the hot Big Bang phase to begin, it might still be continuing in other regions, and these eternally inflating regions continuously spawn new bubble universes like ours. When inflation randomly ends in small pockets, creating what's called a bubble universe or pocket universe. Each of these bubble universes could potentially have different physical constants and even different physical laws, depending on how the fundamental forces separated and how various fields settled into their ground states during the inflationary phase, which means that some universes might have stronger or weaker gravity, different masses for electrons and quarks, different strengths for the electromagnetic force, or even completely different numbers of spatial dimensions. In most of these bubble universes, with different physical constants, conditions would be completely hostile to life as we know it, because stars might not be able to form, or atoms might be unstable, or nuclear fusion might not work properly. But with infinitely many bubble universes being created, some tiny fraction would have physical constants similar to ours that allow for the formation of complex structures like galaxies, stars, planets, and potentially living organisms. This leads to what's called the anthropic principle, which observes that we necessarily find ourselves in one of the rare universes where the conditions allow for our existence, not because those conditions are special or designed, but simply because we couldn't exist in any of the far more numerous universes where the constants don't support life, making our apparently fine-tuned universe potentially just a selection effect, rather than evidence of any deeper principle or purpose. The third type of multiverse comes from quantum mechanics, specifically the many worlds interpretation, originally proposed by physicist Hugh Everett in 1957, which suggests that every time a quantum measurement occurs, or any quantum event happens with multiple possible outcomes, the universe splits into multiple branches, with each possible outcome actually occurring in a different branch. This means that when you flip a coin and it lands heads up, there's another universe that's split off from ours at the moment of the flip, where the coin landed tails up, and both versions of you continue existing in their respective universes, completely unaware of each other's existence, because the branches never interact after splitting. The number of universes in the many worlds interpretation grows exponentially with every quantum event, and since quantum events are happening constantly at every point in space, the total number of parallel worlds would be absolutely staggering, far exceeding anything we could possibly count or comprehend, with new universes branching off at every instant in response to every quantum interaction occurring anywhere in spacetime. String theory, which attempts to unify quantum mechanics and general relativity by proposing that fundamental particles are actually tiny vibrating strings rather than point-like objects, gives rise to a fourth type of multiverse through what's called the string theory landscape, which represents all the possible ways that the extra spatial dimensions predicted by string theory could be compactified or curled up. String theory requires 9 or 10 spatial dimensions, depending on the specific version, but we only observe 3 spatial dimensions in our everyday experience. So the theory suggests that the extra 6 or 7 dimensions are curled up so tightly that they're invisible at the scales we can probe with our experiments, and the specific way these dimensions curl up determines what physical laws and constants we observe in our universe. Calculations suggest there might be approximately 10 to the power of 500 different ways to compactify the extra dimensions, which would mean 10 to the power of 500 different possible universes in the string theory landscape, each with its own unique combination of physical laws and constants. And if eternal inflation is also true, then each bubble universe could randomly select one of these 10 to the power of 500 possibilities when it forms, creating a vast ensemble of universes, exploring every corner of the string theory landscape. Some versions of the multiverse theory suggest that different universes might have completely different numbers of spatial dimensions, not just the 3 we're familiar with, and physics in a 2-dimensional universe or a 4-dimensional universe would be dramatically different from what we experience, potentially making stable atoms impossible or preventing the formation of complex structures needed for life and consciousness. The philosophical implications of the multiverse are profound and sometimes troubling, because if everything that can happen does happen in some universe somewhere, then concepts like choice, responsibility, and meaning become more complicated. Though most physicists argue that these concerns are unfounded because we can only experience and affect our own branch of reality, regardless of what's happening in parallel universes we can never interact with. The major scientific criticism of multiverse theories is that they might be unfalsifiable, meaning there's no way to test or disprove them through experiments or observations, which would make them more philosophy than science according to traditional definitions. But proponents argue that the multiverse is a natural consequence of our best theories of physics, like inflation and quantum mechanics, and we should take seriously what our most successful theories predict, even when those predictions involve things we cannot directly observe. Some scientists have proposed ways to potentially test multiverse theories indirectly, such as looking for subtle patterns in the cosmic microwave background radiation that might indicate our universe collided with another bubble universe in the distant past. And in 2010, a team led by physicist Stephen Feeney claimed to have found possible evidence of such collisions in data from the Wilkinson Microwave Anisotropy Probe satellite, though these claims remain controversial and were disputed by later analysis of more precise data from the Planck satellite. Another potential way to test the multiverse involves measuring the values of physical constants with increasingly high precision and trying to understand why they have the specific values we observe, because if those values turn out to be arbitrary with no deeper explanation, that might support the idea that we're in just one universe selected from many possibilities. Whereas if we discover fundamental principles that uniquely determine the constants, that would suggest we don't need a multiverse to explain them. The energy scale of the multiverse as a whole, assuming it exists, would be literally infinite if there are infinitely many universes, making it by definition the most powerful thing in existence. Though it's important to note that this power isn't concentrated in any one place or available to do work in the way we normally think about energy and power. Each individual universe in the multiverse would presumably be causally disconnected from all the others, meaning that no information or influence can pass between them. So even though the total energy might be infinite, it's fragmented across infinitely many separate domains that can never interact or combine their power. Some versions of multiverse theory, particularly those based on eternal inflation, suggest that the multiverse has no beginning and no end in time, existing eternally with new universes constantly being created as inflation continues in various regions, while old universes expand and cool and eventually fade into darkness, creating a kind of cosmic ecosystem where universes are born, evolve, and die in an endless cycle. The concept of the multiverse forces us to reconsider what we mean by the universe and whether that term should refer only to the region of space we can observe and interact with, or whether it should encompass all of physical reality, including regions forever beyond our reach. And this isn't just a semantic question, but touches on deep issues about the nature of existence, causality, and what we can meaningfully say exists if we can never observe or interact with it. If the many worlds interpretation of quantum mechanics is correct, then there are versions of you in other branches who made different choices at key moments in their lives, leading to completely different outcomes. And while this might sound like it diminishes the importance of our choices, it actually doesn't, because you can still only experience one branch, and your choices determine which branch you experience, even if other versions of you experience different branches. The multiverse idea has profound implications for the question of why the physical constants in our universe seem fine-tuned to allow for life, because in a vast ensemble of universes with different constants, it's no surprise that at least some would have the right combination to support complex chemistry and biological organisms, making what appears to be an improbable coincidence actually an inevitable outcome of exploring all possibilities. Critics argue that invoking the multiverse to explain fine-tuning is giving up on finding deeper physical principles that might explain why the constants have their observed values, essentially replacing one mystery with an even bigger one. But supporters counter that we should follow where our best theories lead, even if the destination is more complex and stranger than we initially expected. The total information content of the multiverse, if it contains infinitely many universes, each with its own complete history and evolution, would also be infinite, raising fascinating questions about the relationship between information, consciousness, and physical reality that philosophers and physicists are still grappling with today. Some theorists have proposed that different universes in the multiverse might be connected through wormholes or other exotic structures in spacetime, potentially allowing for travel between universes in principle, though such travel would likely require technology so advanced that it might as well be impossible. And it's equally possible that the laws of physics absolutely forbid any causal connection between separate universes, making them forever isolated from each other. The ultimate fate of our universe, whether it ends in a big freeze, a big rip, or some other scenario, becomes less significant in the context of the multiverse, because even if our specific universe eventually becomes cold, dark, and lifeless, the eternal process of universe creation would continue elsewhere, ensuring that somewhere in the vast multiverse, new universes are always being born, and new possibilities are always being explored. Whether the multiverse actually exists remains one of the biggest open questions in physics and cosmology, and answering it definitively might require revolutionary new theories or observations that we haven't even imagined yet. But the sheer conceptual power of the idea that our universe might be just one bubble in an infinite ocean of realities represents perhaps the most dramatic expansion of human perspective since Copernicus first suggested that Earth wasn't the center of the cosmos. We've journeyed through the most powerful forces and phenomena that exist in our cosmos, from the strong nuclear force binding quarks together inside every atom with power 100 trillion times greater than gravity, to gamma-ray bursts that release more energy in 10 seconds than our sun will produce in its entire 10 billion-year lifetime, to supermassive black holes containing billions of solar masses that warp spacetime itself into impossible geometries, to dark energy comprising 70% of the universe and tearing space apart with accelerating expansion, to neutron stars with magnetic fields 1 trillion times stronger than Earth's, to theoretical extremes like cosmic strings and vacuum decay that could slice through planets or destroy reality itself, to the Big Bang that created space and time from nothing, to the possible multiverse containing infinite universes with infinite possibilities. And yet, after exploring all these incomprehensible displays of raw cosmic power, perhaps the most powerful thing in the universe isn't any of these extreme phenomena, but something far more subtle and far more miraculous that emerges not from brute force, but from exquisite complexity. Consider for a moment that the universe spent 13.8 billion years evolving from a hot, dense plasma of elementary particles into increasingly complex structures, starting with the formation of the first atomic nuclei just 3 minutes after the Big Bang, then waiting 380,000 years for the first neutral atoms to form during recombination, then another few 100 million years for the first stars to ignite fusion in their cores, and several 100 million more for the first galaxies to assemble from merging protogalaxies. And throughout this entire cosmic evolution, the universe was exploring possibility space, trying out different combinations of matter and energy, creating new emergent phenomena that couldn't have been predicted from the fundamental laws alone. The same physical laws that govern the behavior of individual quarks and electrons somehow give rise to nuclear fusion in stellar cores, which creates heavier elements like carbon, nitrogen, oxygen, and iron that make complex chemistry possible. And these heavier elements get scattered through space by supernova explosions and eventually accumulate in the disks around newly forming stars, where they coalesce into rocky planets. And on at least one of these planets orbiting an ordinary yellow dwarf star in an unremarkable spiral galaxy, something absolutely extraordinary happened that represents perhaps the universe's greatest achievement. On this planet we call Earth, the laws of physics and chemistry that govern everything from quarks to galaxies somehow produce self-replicating molecules that could store and transmit information. And these molecules evolved through natural selection over billions of years into increasingly complex organisms, and eventually into creatures with nervous systems capable of processing information about their environment, and finally into beings with brains complex enough to develop consciousness, self-awareness, abstract thought, language, science, mathematics, art, music, philosophy, and the ability to ask questions about where they came from and what their place is in the grand cosmic story. You are the product of 13.8 billion years of cosmic evolution, made from atoms forged in the hearts of dying stars billions of years ago, assembled into molecules through chemistry that emerged from quantum mechanics, organized into cells through biology that emerged from chemistry, structured into organs and systems through development that emerged from biology, and integrated into a conscious mind capable of understanding at least some of the universe's fundamental workings through neuroscience that emerged from everything below it. And this hierarchical emergence of complexity from simplicity represents a kind of power that's fundamentally different from the raw energy of gamma-ray bursts or black holes, but arguably far more profound. The fact that the universe can create structures capable of understanding the universe itself is perhaps the most remarkable thing that's ever happened in all of cosmic history, because it means the cosmos has become self-aware, that matter and energy, organized according to physical laws, have somehow produced minds capable of contemplating those very laws and their own existence, making you and every conscious being not just part of the universe, but the universe